Hello again. Welcome to the second part of the tutorial on calculating aeroacoustic noise using Ansys Fluent. In this video, I'll explain how to set up the simulation. Please make sure to watch part 1 first. It's time to set up the model. I'll double-click on Setup and hit Start. After a moment, this window will appear. As you can see, the green surface represents the inlet, while the black surfaces with arrows indicate the outlets. The walls are also red and without arrows. In this example, the airflow is considered compressible, so I must apply that setting from the material properties. I'll locate air and double-click on it. Since the fluid is compressible, I need to change the density from constant to ideal gas. After making the change, I'll click the Change button. The energy option is enabled because, in the ideal gas model, density depends on temperature. Next, let's proceed with setting up the boundary conditions. I'll expand the boundary conditions section and double-click on the inlet. Since I don't have mass flow or inlet velocity values, I'll specify a velocity of 20 meters per second. Now, let's check the outlet surfaces. They're selected correctly. The default setting for the outlet is 0 gauge pressure, which is appropriate for this model, so I won't need to change it. Everything looks good so far. I'll proceed to explain the solver in the Methods section. In this section, there are two schemes for compressible flow, coupled and piezo. Let's solve it with the coupled scheme. The speed of air is not very high, so we can disable the pseudo-time method. I'll leave other options unchanged. In the controls section, it's necessary to decrease the Courant number to increase the convergence speed. I won't change it because I'd like to demonstrate what happens during the solution. Let's move on to initialization. Each solution requires an initial guess. In my experience, it's better to use standard initialization for internal flows. I will select the inlet and click on Initialize. The model has now been prepared. I'll go to Run Calculation, specify 50 iterations, and then click on Calculate. As you can see, the solution didn't converge because the Courant number is too high. I'll change it to 5, which is sufficient for Aeroacoustics. I'll click the Calculate button again and wait for the solution to finish. The solution is now complete. The residuals are proper and near the convergence. I recommend solving the model in steady state and then switching to Transient. Now it's time to prepare the aeroacoustic solution. I need to change the viscous model to LES or DES because these two models are used for aeroacoustic solutions. Let's select LES as an example. LES requires a highly refined mesh to resolve generated noise accurately, so I highly recommend investigating the mesh dependency of the solution. The solution converts to transient automatically because LES and DES are transient models. In the Methods section, as I mentioned before, we have to choose between piezo or coupled scheme. Piezo has a lower computational cost for compressible flow and is suitable for aeroacoustics problems. It's very important to change from first order to bounded second order. This change is compulsory. I will not change any other options. Also, I won't modify the under-relaxation factors. I will now go to the Run Calculation menu. We need to specify the time step size. I'd like to check the solution convergence, so I'll specify 10 for the number of time steps to track the residuals. Finally, I'll click on Calculate to solve the model. The solution converges completely in one iteration because I used the stationary solution before. The solution is now complete. Now we can enable acoustics. I will click on Acoustics and select the Ffowcs Williams-Hawkings model. Check the option to export acoustic source data from here. There are several zones in this window. I'm not sure which one is the permeable surface, so I'll look for it in the internal boundaries. The first one is the permeable surface. As you can see, We can only display this domain, so I will select it and click on Apply. Now it's time to add microphones. I'll click on the Receivers button and specify 4 microphones. I've located the air muffler at the origin because I want to specify microphones relative to this origin. The placement of the microphones is arbitrary. Be sure to use a finer mesh and verify mesh independence as well. I think 4 microphones should be sufficient. I'll click on OK to confirm and apply the modifications. Everything looks good. Now we have 4 microphones and 1 permeable surface. We only need to solve this solution. For example, let's solve it for 200 time steps. 200 steps correspond to 0.01 seconds, providing a frequency resolution of 100 Hz. I'll wait until the solution has been fully computed. The solution is complete. Let's extract the acoustic signals by clicking on this button. Select all active source zones, receivers, and source data files and hit on Compute. As you can see, sound pressure signals are saved in all microphones. I'd like to see the sound pressure level with respect to frequency. I'll expand plots in the Results section and double-click on FFT. This is a fast Fourier transform of results. Then I'll choose the process receiver. We can select each microphone which we want. I'd like to choose Receiver 2. Then I'll click on Plot FFT. This is a power spectral density diagram, and I'd like to plot the sound pressure level. We can select it from this drop-down menu. The resolution of frequency is too low because only 200 steps are solved. More steps must be solved. For example, I continue the solution for another 300 steps to see better results. I'll click on Compute again. The solution is complete. It's time to extract acoustic signals. There are 2 source data files now. By default, each 500 steps create a new file. The new solution replaces the previous one, and the frequency resolution is now 40 Hz. I'll go to FFT and plot the sound pressure level again. As you can see, the plot is more detailed. It's better to continue the simulation until the frequency resolution reaches 10 Hz. This video concludes here, and you've learned about aeroacoustic noise using the Ffowcs Williams-Hawkings method. Please follow my channel to watch more videos. Thank you for watching.